In chapter 22, we learned about what makes an electromagnetic wave, and we looked at the different types of electromagnetic waves. One of the most primary types is light. Here in chapter 23, we are going to focus more on light, and we're going to look at some of the geometric optics of light. Now, I'll say right here, these principles work for any type of electromagnetic wave. Light is just the most common type that we work with. In this particular video, we're going to start off by talking about the law of reflection, and we'll talk about the simplest type of mirror, that is a plane or flat mirror. Now, we've talked about light being a wave. So we have had a wave. Oops, sorry, my pen. There's my pen. So light moves along as a wave, but another very good way to describe the motion of waves is not by these wave symbols, but using light rays. This is the ray model of light. So whenever you see a light wave like this one down here, just know that that's really just a wave of light moving forward. So sometimes the wave model of light is more useful. Sometimes the ray model of light is more useful. In this chapter, the ray model is going to be much more useful. It'll help us a lot with geometric optics. When we get into chapter 24, we will want to go back to the wave model of light and use that there. Anyway, so here's one reason why it's useful. It's really good at showing how light from an object can go in all sorts of directions, and how we see the wave enters into our eyes, and having entered into our eyes, our brain can interpret what's going on and gives us an image that our brain can interpret. The basic law of reflection says that as light comes into a surface, it's going to do one of three things. One is it's going to be absorbed by the surface, in which case it would heat up. Two, it would pass right through the surface at some different angle. That's refraction, which we'll talk about later. Or it's going to bounce off and reflect. When it bounces off and reflects, then the angle at which it came in is going to be exactly the same as the angle of reflection. Notice how I'm measuring this angle. I have a line that's normal to the surface. Normal means perpendicular. So we have a line that's normal to the surface, and we always measure the angle of light from the normal line. There's a very good reason for this. In calculus and other forms of advanced math, it makes a lot more sense. Anyway, so the law of reflection says that the angle of incidence, or the angle of incoming light, has to equal the angle of reflection, or the angle of reflected light. And that's always the case, but sometimes you may not have an even surface. If you don't have an even surface, well, light will come in, even if the light is uniform, the light will come in and it'll be really sporadic, because since the surface is uneven, you may have a perfect law of reflection there, a perfect law of reflection here, perfect law of reflection here, but every time the surface is at a different angle, which causes the reflection to happen at a different angle as well. When this happens, the light is scattered around, and anybody can see it, as you can see on the left. The light's scattered in all directions, and so this person up here can see some of the light rays from that object, while the person down here sees other light rays from the object, the result being both of the people can actually see the object. They can see that light. But now let's assume that you have a very flat perfect mirror. So this is extremely flat. There are no imperfections at all on the surface. Well, when the light comes, it's going to obey the law of reflection, so they're all going to reflect at the same angle they come in, which means this person over here is going to see the light, but this person won't see a thing. You could try this. You could put a mirror on the floor, have one person stand on one side of the mirror, another person stand on the other side of the mirror, and then you stand in the middle. Have the two people on each ends move around till they can see each other in the mirror, and they'll say, hey, I can see you, but you won't see them at all because being in the middle, the reflection passes right past you. Now, what you see when you look into a plane or flat mirror is an image. Basically what's happening is light comes up, bounces off of this reflective surface, and comes into your eye. Now, all of your light, you have light coming from the whole bottle. We often just talk about coming from the top or bottom just to illustrate. But light's coming from the whole bottle, and all that light's reflecting off of the surface, coming into your eye, and your brain says, oh, I see light coming from coming in this direction towards my eye. Therefore, the light must be coming from over here. And I also see light coming this direction, so the light must be coming from over here. And so your brain interprets that light as if it came from that location right there. And that is what an image is. Obviously, the object's not there. The reflected bottle here in the picture is in front of the mirror. It's not behind. But your brain is fooled into thinking there is something back there. This particular example is something that we call a virtual image. A virtual image is an image that happens in a place where light does not go through it. So in this case, all the light was happening on the left side of the mirror, but the image appeared on the right side where none of the light's actually happening. So this is a virtual image. With a plane mirror, the object distance, which is the distance from the mirror to the original object, is going to equal the distance from the mirror to the bottle. So they're going to equal each other. So we would just say for a plane mirror, the object distance is equal to the image distance.